So today we're extending the definition of position in 2 and 3 dimensions, and I'm curiously showing you how it could be both right and wrong when describing your location. Stick around. Okay, a firefighter is standing on the ground under the left pillar of an elevated bridge. The pillars are 6 meters apart and 5 meters high. Meanwhile, a rock climber is strapped on top of the right pillar, crying out for help. I'm 6 meters east of the base of the left pillar. Very good. According to this guidance, and since this east fixes the horizontal direction, the firefighter must follow this line up to 6 meters. But, boom, they don't meet. Is this description incorrect? Of course not. In terms of east, the statement is true. Why? Because in this direction, both share the same 6 meters. And then, what the heck? How can my reasoning be correct and not working at the same time? It is because being correct doesn't necessarily mean being effective. And effectiveness is worth more than bars of gold. Something is missing here. Okay? The surgical description should go like this. I'm 6 meters east and 5 meters above the ground. Now, the firefighter goes here, 6 meters, 5 meters, and they meet. Very good, perfect. What was messing up here was this 5 meters up being left behind. This means this statement is true but incomplete. And this gets to the heart of how science really works. Correctness alone may not always be enough. We must be effective, okay? So now, in order for this to be clear, we're x-raying both descriptions to see their visual frameworks, okay? Their graphs. And as we can see here, the graph of the first description is this one. Now, the tip of the arrow is here and the rock climber is there off to the side. This clearly shows that this first case doesn't properly describe the exact location of the rock climber here. Okay, so we're migrating to the second case. Now, the tip of the arrow here and the location of the rock climber are now coincident. It shows that this second case perfectly addresses the exact location of the rock climber here, as confirmed by the graph. 6 meters here, 5 meters up. And the position vector is this one, given by the equation. 6 I hat plus 5 j hat. This is a clear sign that this case, the second one, the right one, should be represented in 2 dimensions, okay? The first case is correct, but misses some information here. This is only 1D. So we are using here 2D. Okay, there's something I need you to write down there. We don't use cardinal points to describe vertical direction, okay? North, south, east, and west are cardinal points we only use to describe horizontal surface here on Earth, okay? So up and down are vertical directions, okay? That's why we have here 6 meters east, a cardinal point, and 5 meters above, up. It is a vertical direction, okay? Okay, and now, since we're all aware that space is 3-dimensional, I believe it won't be uncomfortable to get to know that this graph here will grow another leg, another x, okay? Because now we are graphing 3D position vector. Okay, how can we do that? Very simple. Imagine that a particle is not constrained to a particular dimension, but rather it just keeps sweeping all around, varying its position over time. In a given instant, that wandering particle will be occupying a point P, given by the coordinates x, y, and z. So we draw 3 x's here, okay? X, y, and z. And these are unit vectors defining positive directions. I hat points to x positive, j hat to y positive, and k hat to z positive, okay? So we're gonna use here parallelogram theorem, okay, to draw this position vector. So first I draw here a dashed line that would be parallel to yx, okay? Another dashed line parallel to x-axis. So the correspondence of those axes will give us a mini vector, okay? And we are not done yet because we haven't used yet these axes, okay? Now we are getting rid of these axes here because we have already used them, okay? So this mini vector here joins forces with this x here so that we draw a dashed line here that will be parallel to zx, okay? Another dashed line here parallel to what? To this mini vector. And that correspondence, the correspondence of these two axes will give us the final result, okay? Which is the position vector of this wandering particle here, okay? Yes. So position vector over time is this. So how can we write the expression for this position vector? Very simple. That position vector will be given by the sum of the coordinates in each x, okay? So this will be xt, y will be yt, and zt. So that summing up this, we'll have here xt, I, yt, j, and ztk. So this is the position vector of this particle varying with time, okay? And now for a stationary object, kind of taking a peek of this stubborn wandering here, since that photo would be just capturing a moment, this position vector that varies with time will be a constant, okay? For a stationary object here, this varying position vector here with time will simply be a constant. This means we write this. We have here xi, so time get lost here, plus yj and zk. This is the position vector for a stationary object, okay? And this simply allows you to find the magnitude or the length of this vector, okay? Very simple. How can you do that? If you look carefully, you'll see that this is the right triangle here, okay? And the position vector here is the hypotenuse of this triangle. So we'll use Pythagorean theorem here to just find this length of this vector here. Before that, we label this base as B and the height is A. So now we need the length, okay? Or magnitude of this position vector. Okay. So applying that theorem here, we'll have here position vector squared, okay, will be the sum of A squared plus B squared, okay? And position vector equals A. What is A? A is the zx, so we'll have here zk squared plus B. What is B? B is this base here, okay? But this base here, okay, is the hypotenuse of another right triangle here, okay? So applying Pythagorean theorem here again, we'll have B squared equals what? This length, which is x, xi squared plus this length, which is y squared here. So we'll copy and paste this expression here. xi squared plus yj hat squared. Okay? This is a very simple arithmetic here. But before that, we know from the dot product that I hat squared equals k hat squared equals j hat squared equals 1 from the dot product. So that position vector here will be z squared, okay, k squared equals y squared equals j squared, 1. So this k, I, and j vanish from the equation. So that we have z squared plus x squared plus y squared. So in the standard form, we can write position vector squared equals x plus y plus c. So that the length will be square root of this sum. Okay, x, y, and c. So this is the magnitude or length of this position vector here. So, very good. In order for you to apply what we've learned here, we're going to solve a simple example here. Okay, graph the position vector of this r equals minus 2i hat plus 3j hat plus k hat. So what I'm going to do here is not using the parallelogram method as we did earlier here, because I want to make it much more simple, okay? How? We have this axis, we have here a positive zx and the corresponding negative x, okay? Positive here, negative y, positive x, and negative x. Minus here, minus, minus. Okay. So, minus 2i hat is x-axis, okay? We have here. This is 1i, 2i, 3i. Minus 1, minus 2, okay? So the first point is this. And from this onwards, we're going to write this y here, okay? So we'll start from this point. We can start from the origin. Otherwise, we'll be obliged to use the parallelogram theorem, okay? We start from this point and write 3j hat, okay? 1, 2, 3j hat, this length. So this will be something like this, okay? This point here. Okay, drawing here 3j hat, okay? Yes, this is another point, 3j hat, okay? And finally, k hat. This is zx, okay? Zx, okay? K hat equals 1 k hat. So we're going upward here and just draw here a k hat. This is another point. So the tip of this length here and the origin will give us the final result, the final position vector of this equation. So here we go. So the position vector R is this one, And the equation is this, okay? And that's that. We are done now. I hope you like what you see. See you the next time. Take care.